I think let's get started now. And good afternoon, everyone. Thanks for joining us this on-demand webinar, a part of the wind workforce development effort here at NREL. We are very excited about our first webinar of this series. Our presenter today is Liz Walls, and the topic is wind flow modeling over complex terrain using Continuum 3. Educational tools and curricula to support university education are part of NREL Windforce development effort. This NREL project aims to enhance classroom activities at Wind Application Center and universities. Lisa Walls is joining us today from Ohio. Thanks Heidi Tennyson for her help to put it together. I got an opportunity to learn wind flow model underlying Continuum while I was working in industry back in 2007. I worked then with Jack Klein at Horizon Wind. Liz developed Continuum software from an idea to state-of-art wind flow modeling and analysis software. And especially I like the plug and play feature of Continuum 3, and obviously its availability in the public domain. I can only guess efforts Liz might have put there for such an automation. Continuum 3 has incorporated advanced functionalities such as turbine time series analysis, hourly energy production report, and many more. And I'm pretty sure Liz will highlight them. We'll try to make this webinar as interactive as possible. Please use chat feature on Zoom so that you can submit your question to us. Please go to chat and type your question there. You have an option of asking the question to everyone or the specific person. Please direct question to everyone or Liz Gills. She's helping us today to put this question together. In any case, please keep your question coming. With that, I'm going to hand it over to Liz Walls. Liz, you can start. Thank you.
Great. Thanks for the introduction, Ron. All right, so to start, I think we need to share my screen. Well, good afternoon, everyone. As Ron mentioned, my name is Liz Walls, and today I'm going to be talking to you about wind flow modeling in Continuum 3. So first of all, quick introduction. As mentioned, my name is Liz, and I'm the creator and developer of the Continuum wind flow modeling software. My background is mechanical engineering. I have a master's from UMass Amherst, where I studied in the Wind Energy Center in 2005. And I've been working in the wind industry since then, since about 2007. I started working on Continuum back in 2011, and the objective back then was to create an intuitive, easy-to-use, plug-and-play software that would quickly deliver accurate energy estimates. Since then, I've been awarded 2 US patents for the wind flow modeling algorithm behind Continuum, and then in 2015, the software was acquired by One Energy. And then since then, been working really hard to get Continuum 3 released, and that happened just last October. And we uploaded it to GitHub, so it is now officially an open source resource. And the objective of this release was to get Continuum 3 out there to encourage collaboration to further advance the tool, as well as advance the accuracy of the wind flow model. So now let's talk about the outline of today's webinar. First of all, we're going to do a quick overview of wind flow models. Then we'll talk specifically about Continuum. We'll talk about how the model is derived both from a simplified analysis of Navier-Stokes, as well as using the log law surface roughness model. Next, we'll talk about how those two, or how the wind flow model is applied in the software. Then we'll jump into Continuum 3 and give an overview of the software. We'll talk about the various inputs that are needed, the different features and functionality, as well as how to install the software and where to find the source code. Then we'll get into a demo of Continuum. And as Rob mentioned, Continuum 3 can do a lot of different things. So we're going to focus on a specific task here, which is to create a wind flow model, generate turbine estimates, and then create a wind speed map. And then finally, we'll open it up to some questions. All right, so let's jump into it. So first of all, what is a wind flow model? Well, it's a model that allows you to predict spatially how the wind speed will vary across a project area. And model inputs for wind flow model typically include topography or digital elevation data, as well as land cover or some measure of surface roughness. What I'm showing down here is a map of land cover codes, which we'll talk about later, which can be used to estimate the surface roughness. And then you also need some measured wind speed and wind direction data at one or more met sites. So here we have wind speed distribution and then the windrows. Now, there are a few different types of windflow models out there. We're going to talk a little bit about that. But really, something to know is that at the end of the day, essentially all the models, all windflow models are based in one way or another on Navier-Stokes. And for those non-familiar, Navier-Stokes is a set of equations that define equations of motions of a fluid due to various external and internal forces. Now, these different windflow models can be categorized in different types. And here they are listed from most complex to simplest. First, we have direct numerical simulation. Then we have large eddy simulation, computational fluid dynamics, and then a category that people refer to sometimes as linear or just simplified. Now, obviously, the more complex models will have a higher computational requirement. As an example, GNS models can require days, sometimes weeks, depending on how large your area is to run. On the other hand, linear models can be run in minutes. So as you can imagine from an engineering standpoint, having a linear model that can generate estimates in a few minutes is pretty desirable. Continuum falls in that category. Continuum is based on a simplified analysis of Navier-Stokes. So now let's get into how Continuum's model can be derived from Navier-Stokes. Before getting into that though, sorry, jumped ahead of myself, we want to talk a little bit about complex terrain and how Continuum models it. So first of all, what is complex terrain? Well, really, it can be defined, terrain can be defined as complex if there are either or both significant variations in the topography or the land roughness. So in Continuum, to model complex flow, we use a simplified version of Navier-Stokes to model how the wind speed will change due to varying topographic variations. And then, so there's the Navier-Stokes equation. And then we will also use the log-law shear profile to estimate the change in wind speed due to changes in the surface roughness. Okay, so now let's talk about Navier-Stokes and how the Continuum model can be derived from it. So Navier-Stokes, it is based on Newton's second law of motion, and it has to do with the conservation of momentum, where if you have a moving fluid or object, the change in momentum is equal to the sum of the forces acting on that object or fluid. And the acceleration of that is directly proportional to the net force acting on it. So I'm sure everyone is familiar with this very simple equation. This is what Navier-Stokes boils down to it under simple conditions. So it's just the force equals mass times acceleration. The full expression in Navier-Stokes expands the force and acceleration terms, where on the left-hand side you have acceleration, where it is time dependent as well as dependent on the Cartesian x, y, z coordinates. And then you have on the right-hand side the various forces that can act on that fluid. So with wind, we have pressure gradient forces. We also have shear due to the roughness of the terrain. And then we have gravity. So in defining the model for Continuum, we use the control volume approach, which is used in mechanical engineering. So essentially you define an imaginary surface, and then you treat that imaginary surface like a free body diagram where you examine the various forces acting on the control volume. Then you can sum up those forces to determine the acceleration of that control volume. So let's look at a situation where we have a blob of air that's traveling downhill. So if we look at this blob of air, we can look at the different, or we can draw out the different forces that are acting on it. First we have, well, I should mention the wind direction is going from the left to the right. So we have Px, which is the horizontal pressure gradient force. So that's pushing the wind to the right. We also have Pz, which is the vertical pressure gradient force. Then we have tau, which is the shear force, and then the force of gravity. So if we sum all those up and then we have the angle of the terrain, then we can have the Navier-Stokes equation expressed here, which is summing up all the different forces acting on that control volume. So with that defined, now consider a scenario where we have two sites. At site 1, we have a wind speed that is known, and at site 2, we want to estimate that wind speed. So the acceleration at the two sites, just writing up the same equations as the previous slide. This is saying the acceleration of the wind at site 1 will be the sum of all these forces, and then the acceleration at site 2 will be the sum of those. So now, here comes some of the simplifying assumptions. So in many cases, we are modeling a project area where a lot of the conditions are very similar. So if we can say that the density and the surface roughness and the atmospheric stability are all uniform, and the shear forces at the two sites are approximately equal, then we can so tau1 approximately equals tau2, then we can equate these two equations to the following. So now we're looking at the difference in acceleration, and then we have some pressure gradient forces and the force of gravity, and this is the change in the angle in the downwind terrain between the two sites, delta cos, and this the theta, that is the angle of the terrain. So you can see the different forces as a function of the terrain slope. Now, since in wind and topography, cos theta is going to be much, much smaller than sine theta, then this first term can actually drop out in most cases. And then it simplifies to this equation here. So again, it's defining the difference in acceleration between the two sites. Taking it a step further, if we then expand the acceleration term using the material derivative, then the same equation takes on the following form. Next is, so again, this is acceleration, acceleration 2, acceleration 1, and this is the same term from the previous slide, where the force of gravity, the force of the pressure in the vertical component, and then the change in the downwind terrain. Now, some more simplifying assumptions. If we assume steady state conditions and 2D flow, then we can eliminate these terms. And now we have delta Vx, delta x, and delta Vz dz. And those describe the rate of change of velocity in the x and z directions. If we assume that those are equal, then we can combine those terms to this simplified equation. So now we have the wind speed at site 2 estimated as a function of the wind speed at site 1 plus the change in velocity due to the change in the downwind terrain. Now, right now we're dealing with angle, but through a lot of different testing and empirical analysis, it turns out that instead of using just the angle, we use what is called exposure, which I'll talk about in a minute. But what's important to know from this is that we have this expression where we have gravity, the vertical pressure gradient force, and the flow field wind distribution. But it turns out that all these variables can be condensed down into one single coefficient m. Okay, exposure. Oh, sorry, I should mention that this function m, this coefficient m, is a function of the terrain complexity. It's also a function of atmospheric stability. So it can vary from site to site and during different atmospheric stability conditions. Now, what is terrain exposure? Just real quick. So the exposure is defined as the average elevation difference between a site and the surrounding terrain weighted by the inverse distance. This is the equation for it. And just as a couple examples, with the wind blowing from left to right, if we have a met site on top of the hill, then we have a positive exposure in both the upwind and the downwind direction. In this scenario, we have a negative upwind, so the terrain is upwind of the site, and a positive downwind exposure. So again, exposure is a weighted elevation difference, weighted by the inverse distance, and it is used to measure how high or how low a site is compared to its surrounding terrain. Okay, now let's talk about uphill flow, because there's a bit of a special condition that happens in this situation. So if we have wind traveling uphill, so here we have the similar control volume with the different forces acting on it. So when wind is traveling uphill, there can be pressure buildup on the front of the hill, and that induces acceleration. It's called induced speed up over a hill. So if that happens, then you have an increased PZ, an increased force pushing the air up, but at the same time, you have gravity and the shear acting against that vertical pressure gradient force. So the point at which those two forces are equal and opposite, where the pressure from the vertical gradient force is equal to the gravity and shear slowing it down, that point we define in continuum as the critical upwind exposure. So if a site in continuum has an upwind exposure less than that critical upwind, then it accelerates. Conversely, if it's greater than that, then it decelerates over hill. And these are the equations that then describe how the wind will change due to upwind terrain changes, depending on whether it is in the speed up flow or if it's in the uphill flow where the wind actually decelerates going uphill. Okay, so then to sum up, these are all of the different upwind and downwind scenarios that we can have, and these describe how the wind speed, change in wind speed can be estimated based on the different upwind and downwind changes. So here we have the equation for how the wind speed will change due to downwind variations in the terrain, and then the second one, how the wind speed will change due to the upwind. Putting those together, one of the main functions in continuum is this simple equation, where the change in wind speed is going to be equal to the sum of how the wind speed will change due to variations in the upwind and how it will change due to variations in the downwind terrain. Now I'd be asking, how do we define these coefficients, m? Let's talk about that a little bit. So through empirical analysis, we found that these model coefficients can be approximated using log law or power relationships, where the x component is terrain complexity. In Continuum, we define 3 different types of flow. There is downhill flow, uphill, where the wind decelerates, and speed up, where the wind accelerates going uphill. So these are the 3 different models, and these are the default model coefficients. The x-axis, as I mentioned, is terrain complexity. I'm not going to get too much into that today, just due to time. But all you need to know is that terrain complexity increases with P10 exposure, and you can see the model coefficients decrease with that. And so what that is saying is that in areas with low exposure or low complexity, the wind speed is much more sensitive to changes in the terrain. Whereas in areas that are more complex, the wind speed is less sensitive, and so an equivalent change in terrain in more complex site will result in a lower change in the wind speed. Okay, so that was the topography portion of the continuum model. Now we're going to talk about how surface roughness is modeled. As I mentioned before, we use the log law shear profile to predict how the wind speed will vary due to changes in the surface roughness. Here we have the log law model. I'm not going to go into it too much. You can Google it later if you're not too familiar. But essentially how this works is that we define the log law at each site and then take the difference between the two. Again, we have site 1 where we know the wind speed and site 2 where we're trying to predict. So if we know the wind speed at site 1, we can solve for the friction velocity, U star, using this equation where we know wind speed 1. And then if you can assume that the friction velocity is approximately the same at the 2, then you can combine the terms to estimate wind speed at site 2. Now the values that are important in this equation are the surface roughness and the displacement height at the 2 sites. Now you might be wondering, well, where do we get those numbers? Well, the answer is using land cover data. So in Continuum, you can import land cover data. If you're working in the US, then the USGS has a publicly available land cover data set that you can download. The data is available on a 30-meter grid resolution, and each data point is assigned a land cover code. And this is the list of different land cover codes that are used in the USGS land cover database. So you can see there's water, there's hay, row crops, and these are all the different land cover codes. So then in Continuum, we take that information and then we have a land cover key that assigns a different surface roughness or displacement height to the various land cover types. And then at each site, similar to how we calculate exposure, we calculate the overall average upwind and downwind surface roughness and displacement height using an inverse distance weighting. So very similar to the exposure, again, to get an overall sense of what the surface roughness and displacement displacement height is upwind and downwind of each site. So to sum up, Continuum estimates the wind speed based on, first of all, a measured wind speed at some site, plus an estimate of how the wind speed will change at site 2 based on variations in the upwind and the downwind terrain, as well as variations in the upwind and downwind surface roughness. Same equation expanded out. So these are our model coefficients, and then we have the log law models. So I mentioned before that we have the model coefficients defined using these power or log-log relationships. Well, it turns out those coefficients can change from site to site. And also, you can, well, let's see here. They can change from site to site. So it made sense when I was developing this tool to use all available metadata to figure out what those coefficients are. And so that leads us next to the site calibration portion of the Continuum model. So what happens in Continuum when you load in your data is it will take all that information, the topography and the surface roughness, and then the default model, and then it will cross-predict, or it will predict the wind speed between each pair of met sites that you have at that project. So you will then end up with wind speed estimate errors at each of those sites, and you calculate the overall RMS, or root mean square error. Then Continuum has a machine learning algorithm that systematically modifies the model coefficient relationships, recalculates the met cross prediction error, and then it does that until it narrows in on the set of coefficients that yield the lowest met cross prediction error, and that defines the site calibrated model. Now this is done for every wind direction sector, and at the end of the day you end up with these 3 relationships for each of the different types of flow. Again, it's downhill, uphill, and speed up over a hill. And you also will define the critical upwind exposure and the stability factor used in the log law roughness model. So then once you have that site calibrated model, you can then use it to predict the wind speed at turbine sites or map nodes. So last bit of continuum theory is how we combine all those estimates. So in actuality, in Continuum, we are creating 4 different site-calibrated models. And the difference between those models is the radius of investigation that is used in the exposure and in the surface roughness calculation. That radius can vary from 4,000 to 10,000 meters, so there are 4 different models. At the same time, each MET site that you use in your model is used individually to generate a wind speed estimate at your turbine or map node. So that means at the end of the day, you end up at every turbine site or map node with a total of 4 times the number of MET sites. That's how many estimates you'll have. So you need a way to combine them all. So the way that it works right now is we assign a weight to each of these estimates. And these weights reflect the similarity in terrain between the predictor and the target site, as well as the root mean square error of the MET cross prediction error of the MET cross prediction for that particular model. So the overall weight is the product of those 2 weights. And then finally, we will generate the average wind speed estimate at the turbine or map node using that weight and each of the estimates generated from each of the models and each of the MET towers. Okay, so now let's move on to model uncertainty. So once you've created this model, of course, you're going to be curious about how, what level of uncertainty to associate with the estimates. And so what is often done is what is called the round robin analysis. Now in this analysis, in the round robin, the way it works is MET sites are systematically omitted one at a time from the model creation. And then with that model, with the MET omitted, you predict the wind speed at that site, and then you measure the estimate error. And you do that for each of the MET sites going in a round robin fashion, and at the end of the day, you calculate an RMS error. And that gives you an indication of the uncertainty of the model. It also gives you a measure of how robust that model is. In other words, if you take one MET site out, does it change dramatically, or does it hold true to the coefficients? In Continuum, there's a round robin capability in the uncertainty tab, which I'll talk about later. Okay, so now you might be wondering, well, how accurate is Continuum? Well, recently I did an internal study where I I created Continuum models at 21 different sites where I had at least 4 MET towers. I conducted a round robin analysis, and then I grouped the models by terrain complexity. And here are the results that I found. So grouped by complexity, you can see that the round robin RMS error is between 1 and 1.5%. Whereas when you get into really highly complex terrain, then things get a little trickier and we have a higher RMS error, just under 3%. So that gives me an idea of what level of accuracy to expect. Okay, so now let's move on to Continuum 3. Talk about the different features and functionality. As Ram mentioned, Continuum 3 is now open source, and it includes several features beyond what Continuum 2 provided. So first of all, so I've broken this into different categories. So first of all, we have the pre-wind flow modeling category. Here, the user can conduct MET data quality control filtering. You can also download MIRA2 data, and that long-term reference data can then be used with MCP to predict the long-term wind resource at a MET site. Next category is wind flow modeling, which we'll talk about more. So the site-calibrated model creation happens in Continuum. You can create gross turbine estimates, you can conduct a round-robin analysis, and you can create wind speed maps and then export as a WRG file, which is used in other wind modeling softwares. The next category is post-wind flow modeling. We now have a Monte Carlo exceedance modeling feature, which is really cool. You can measure, or you can model different losses and uncertainty using different functions in a Monte Carlo simulation. We also now have time series energy estimates and weight loss modeling, where you can use the eddy viscosity or the Jensen model. Then the last category is site suitability, and this is also new in Continuum 3. So now there's a tab for site conditions where you can analyze the turbulence intensity, the extreme shear, extreme wind speed, and the inflow angle at any site. There's also now an ice throw model, which predicts how ice may be thrown from blades. Then we also have a shadow flicker model, which is pretty cool. There's a map now that shows the tower or the shadow flicker from turbines every month, every hour. You can see how that distribution looks, and you can also calculate how many hours of shadow flicker any nearby residents might experience. And then finally, there's also the turbine sound model. So there's a lot of stuff that we could potentially talk about, but today we're just going to focus in on the wind flow modeling aspect of Continuum 3. Okay, before I go any further, this is showing how to get Continuum 3. So there is the Windows installation file is on Dropbox, and here is a bit.ly shortcut address for you to follow to download that install file. Then the second option is if you really want to get under the hood, so you can get the source files from GitHub, and that is the link right there. Okay, so now let's get into a demo of Continuum 3. So I'm going to go over all these different steps of how to create the wind flow model, generate turbine estimates, and then how to create a wind speed map. So obviously the first step is to install an open Continuum, and then you want to save a CFM file right away. The reason you want to do that is because Continuum creates a local database file, and that is used to store all of the calculated values that may be needed but aren't needed right away. It also stores the topography data, stores everything that you upload into a database. So you need initially to save the file in some location so that it can create the local database. Next, you want to import the topography data. Then you want to import the land cover data, and then metadata. And then at that point, you'd run the round robin analysis because at step 5, the wind flow model will have been created. And then you want to import the turbine power or thrust curves. You can import one or several if you like. The turbine sites need to go in there, and then we'll generate the estimates of the turbine sites, and then finally create a wind speed map and export the WRG file. Okay, install, open, and save. So as I mentioned, you can get the installation file from this bit.ly shortcut. You'll need to download and install the SQL Local DB program, which is also in that Dropbox folder. And then install Continuum, and then open it up from the Windows Start menu. And save a .cfm. Okay, so now step 2, import topography. So for topography, it will take the data as either a GeoTIFF or an ADF file. If you're in the US, you can follow this link to download data from the USGS. It used to, they've changed a little bit, the USGS, how things work. Sorry, I'm getting chats. Do I need to look at this chat? Okay, sorry, I had a couple of notes here which we'll address after. Okay, so when you first open Continuum, you'll see this input tab. You'll notice the buttons are red, and those are to help you keep track of what you have imported and what is still required for the model. As I was saying, the USGS used to have a website where you would just enter in the lat long, and then it would crop out exactly the size of topography that you need. They don't have that anymore, unfortunately, so now you have to download tiles of topography data, so you often end up with way more than you need. So at the moment, the advice is to use QGIS, which is the open source GIS software, where you can import those tiles and then crop out just the topography that you need. I should also mention that I'm currently working on a feature that the users can just, through Continuum, download the data that you need. So that's in the works. Okay, so back to the demo here. So we have the Continuum input tab. So we just click import elevation data and bring in the GeoTIFF. And so you can see our topography data plotted here. This is using an open source graphic software called Oxyplot, and it's really great. You can zoom in on areas, you can click on the map anywhere, and it'll tell you the elevation. So that is the topography data, and you can see that the button has turned green to show you that you've successfully imported that input. Okay, the next step is to get land cover data. Again, this is the link if you're in the US for where to download land cover data. And then you can also crop it in QGIS to tailor it just to the size that you want to model. So to import land cover data, the first step you have to do is you have to select the land cover key. So you click this button here and it opens up this dialog. So in Continuum, there are a few different land cover keys that are built in. The one selected here is the US National Land Cover Database. And so there's also one for the North American database as well as for the EU's. You can also import your own key if you're not working in these areas. So you select this key, you click OK, and that shows that you've selected the US National Land Cover Database. And then the next step is to click Import Land Cover. And then that will lead you to import the GeoTIFF, and then that will turn green once it has successfully been read in. Okay, so now that you have land cover and topography data, the next step is to get your metadata. Now in Continuum 3, you can import metadata in a few different ways. The first way is using a tab file, and a tab file looks like this. It is a wind speed and wind direction joint probability distribution. People may be familiar with it, maybe not, but again, that is what it is. And so for each met site, you'd have a tab file that's just describing the wind speed and wind direction distribution at that site. The second option is to input the data as a time series. In this feature, you can import data from multiple anemometers, multiple wind vanes, and temperature sensors. This is an example of that. You can also import multiple heights or just a single hub height. If it's just a single hub height, then Continuum will not extrapolate. Then you can also specify whether or not the data is filtered or unfiltered, and that will tell Continuum if you want to apply the met data quality control filters or not. If you do want to do a time series import, then the headers are specific to Continuum, and so there's a little function in Continuum that allows you to generate those headers. So if you go to the Metadata QC tab and click on this button, Generate Headers, it opens up this dialog. And then here, this is a utility to generate those headers. So you would input, or you specify what type of data you have. If you typically for an anemometer, you would have the average, standard deviation, and the min-max wind speed. You also specify the units of the wind speed. And then for every anemometer, you would specify the height, orientation, and click Add. And also for temperature sensors, you need to select the unit. So in this case, we have Celsius. So you'd enter the Met Tower name, the lat long, the various heights and orientations of your anemometers, heights of your wind vanes, and your temperature sensor. Then you enter in the name of your file, and then click Create Headers. And that creates a CSV with everything formatted, ready for you to paste in your data. Okay, so in this example, we're going to stick with tab files. It's just a little bit simpler, easier to explain. So to start a model, to create a WinFlow model with tab files, on the Input tab, you click the button, Import Tab Files, and then you can select one or many. You can bring in as many tab files in at the same time as you want. And then once you do, it will automatically start the calculations. So here I can show that exposures are being calculated, and then it will automatically go into the site calibration for that model. So the user doesn't have to worry about any settings or how to conduct that calibration. Everything is happening behind the scenes. So then once the site calibration has been completed, then you'll see that these buttons have turned green and the WinFlow model is now complete. So once the WinFlow model is complete, I always like to run the round robin to see how good the model is, what level of uncertainty we're looking at, how robust the model is. So to do that, you go to the Uncertainty Analysis tab. The first thing you want to do, so there's this little drop down here, and it shows you how many MET sites to use. So in this example, we have 3 MET towers. So the maximum is 2. So you can do a round robin using 2 MET sites at a time to generate those models. If we had 5 MET towers, then the options in that drop down would be 4, 3, 2, 1 MET towers. So if we select 2, and then we click Do Round Robin, and then actually in this case, I also selected 1 and did the round robin. And so this is showing the wind speed estimate error of the round robin analysis. So this is using the 2 METs per model situation. So you can see for each model that was created, you can see we used MET 1 and MET 2 to predict at MET 3, and there was a 2.55% error, and so on. And then the RMS of all of those errors is 1.62. And so this was also done for 1 MET tower. So you can actually change this drop down here to look at 1 MET, and then that will show you how the wind speed estimates varied and what sort of error we're looking at using the one MET model, which is actually using the default model coefficients. And then finally, this plot here can be really useful, especially if you have a lot of MET towers and you run the round robin for many different subset sizes. You can see how the RMS error changes with the number of MET sites. In fact, it's really cool if you have 10 or 12 MET towers to do this up to that. You can actually see the error start to plateau, and that's an indication that additional MET sites are not improving your model any further. Okay, so that's the round robin. Steps number 6 now, we're getting into the turbine estimate part of the modeling. So now this is where we import the turbine curve or curves. So you can bring in one or as many power curves that you'd like in order to evaluate different turbine models. So these files are formatted as a CSV, where we have the turbine name in the first row, and then 3 columns showing the wind speed, the power, and the thrust of that turbine. To import that curve, you go to the Gross Turbine Estimates tab and click this button here. See, it's still red because we have no power curves imported. Click that button and then bring it in, and you can see we have our thrust curve in orange and then our power curve in green. And again, you can do that, you can input as many power curves as you like. Now the next step is to import the turbine sites. This is really simple. It's just formatted. The turbine sites file is formatted as a CSV, where you have the turbine name Latin long. So you just bring that in, you click import, and you bring it in, and then you can see our turbine sites appear on the topography map. The next step is to generate estimates of the turbine locations. This is very simple. You can actually do this on the Input tab or on the Gross Turbine Estimates tab. There's a button called Generate Gross Energy Estimates. So you would just click that button. It would run the calculations and refresh this page to show the gross turbine energy estimates that were produced using the wind flow model that you created. So there's a lot of information on this tab. We have the overall wind speed, overall energy production, the capacity factor, Weibull parameters. We have a histogram of the wind speeds at the turbine sites as well as the METs, and the wind speed distributions over here. And then finally, so if you have multiple power curves, you can change this drop down to toggle between the different turbine models to see how the energy production varies. And then finally, there are a bunch of four different export possibilities. So you can export just the overall wind speed estimates there, or the overall wind speeds and energy estimates, or the wind speed distributions, the directional wind speed distributions. So that's step number 9. And then finally, we have, sorry, that was step 8. Now we have step number 9, which is creating the wind speed map. So this is really handy, not only for, well, because they make pretty pictures, but also for identifying areas of good wind to help you figure out what areas you might want to go after for a land lease or for a new project development. So we'll talk about this a little bit. Okay, so on the Maps tab, which is way down over here, if you open it up, it'll look like this. So the first step, you want to just click Generate Map, and it'll open up this dialog. So now we have to specify what grid resolution to use and what min-max UTM-XY to use. So there are a couple of buttons to make your life a little easier. The first one, you click and then it will populate these fields with coordinates that represent the largest possible area to be mapped, depending on how much topography and land cover data you've imported. Or you can click this button and that will create a map that only includes the turbine site. So if you just want to look at the wind speed variability for a defined set of turbine sites, then you might want to use that option. So you click that, click Generate Map, and then after, depending on how big it is, it could be a few minutes, it could be an hour, it could be a couple of hours, depending on the grid resolution, you'll end up with a heat map showing the wind speed spatial variability across your site. So here we have red indicating a high wind area, blue is a lower wind area. So again, creating these images is incredibly useful for understanding turbine placement, wind site, wind farm optimization, as well as for prospecting too, if you model a larger area. And then finally, if you want to export the map as a WRG file, which can be imported into other softwares, so you just click this button. Okay, now let's talk about the future of Continuum. As I mentioned a couple of times now, Continuum is now open source and is available on GitHub. I have a new website, but it is currently under construction, but just a couple of features of what will be included on the website. I've been working really hard at providing detailed documentation of how the software is built, the architecture behind it. Also, in-depth explanations of all the critical functions, so all the functions that are used to generate any part of the energy estimate. There is a document explaining all those various critical functions. There will also be instructions of how to be a Continuum contributor. Because again, the goal of making this open source is to encourage collaboration, get other people thinking about the WindFlow model, how to apply it, how to improve it, and different ideas. And what better way than to make it free? Also on this website, we'll have news and updates on developments. I'm going to have a whole series of instructional videos, as well as an overview of the physics behind all the different models. And just to sum up, there are a lot of different models, so it's going to be a pretty intensive or extensive website. These are all the different models in Continuum. And then finally, I'm showing this email address down here that if you'd like to be added to the newsletter, well, I'll be announcing the launch of the website, or if you have questions about the software, if you download it and are using it, go ahead and feel free to drop me an email at that email address. And that sums it up. Hope you guys were able to understand a little bit about the Continuum model and the physics behind it, how it works, and how it approaches the problem of modeling in complex terrain. And I would be happy to open it up. Let's have a discussion. I'm curious about your questions.
Thank you, Liz, for such a detailed overview of the Continuum. And now I'll open this webinar for a question. Any comments?
Yeah, I got a couple of notes from RS2448. Are they still online? Yes, they are. It says, how is the vertical variation in wind speed modeled? So in Continuum, we are modeling a single height. So this is assuming that your Met Tower data has been extrapolated to, say, 80 meters, if that's your hub height. And then the wind speed, again, is just predicted at that one level. In future editions, I definitely want to expand that to model different heights. And some ideas that we've talked about is just using the power law equation associated with some sort of estimate of atmospheric stability to extrapolate up or down. But at the moment, yeah, it's just a single height. Next question, could we get a link to the Dropbox? I posted that. And then Rob Larson said that it was a little tough to follow. Maybe was I speaking too quickly there, Rob? Or are there any specific things you'd like to go back to? Oh, I don't think he has audio.
Let me open that for, I'm not sure, like,
This is Rob. Was I muted before?
I believe you were, yeah. I can hear you just fine.
Oh, sorry, yeah. I just gave a long answer to my phone and no one else. No, I followed along as best I could and managed to download the software and got running on my machine during the presentation, so I was distracted a little bit.
Okay.
I think that having the slides up on OpenEI will be great.
Okay, great.
We'll make sure that they will put slides and the recording of this video on OpenEI. That's the plan for now, Rob, and we'll update you on that.
Great.
So I just posted another one on chat, but I'll just ask it live. So I've played around, Liz, with the OpenWind software a little bit, mostly the original beta release, and had some assignments with my class, renewable energy class here at Montana State University, messing with that software, and it's not been entirely satisfying. Are you familiar with that software?
I am.
OpenWind. So can you comment on like functionality between the two bits? This Continuum looks like you can control a lot more knobs.
Well, that's the idea of making it open source, is that if you really want to get under the hood, you can control anything, everything. So for OpenWind, it has an interesting history. You know, it started off as an open source software, but then it was acquired by AWS, I think 5 years ago, something like that. And since then, it's no longer open source. It's now, you have to pay for it. And since it has become not open source, I have not personally worked with it very much, but I have a lot of colleagues that do. And from what I understand, it has a lot of great capabilities for optimizing wind farm layouts. And it acts more like a GIS type software where you can put different layers. You can look at the electrical collection lines and things like that Continuum doesn't do. So I guess I would say that Continuum focuses more on the wind resource assessment side, whereas OpenWind focuses more on the wind farm optimization and layout part of things.
Right. So the other piece of software I've been using in my classes is Windographer, which I've been using mostly for the wind resource assessment stuff. So I'm considering after this presentation maybe moving into Continuum for both pieces, since as you mentioned that OpenWind is now not quite as readily available, and Windographer I need to get a new site license. So
yeah, Windographer is actually owned by the same group now. AWS bought Windographer around the same time, around 4 years ago. And yeah, so Windographer does a great job at displaying data, and its main functionality, as I'm sure you know, is for quality control and for filtering out bad data. Whereas Continuum has that feature now, so it has MET filters. But what's really great, I think, especially from an educational standpoint, having that data, having the source code open source, is that students can think about different ways to filter the data, or different ways to flag icing, you know, and they can themselves implement those changes in the code and see what happens. So yeah, that's fantastic, Rob, to hear that that you're thinking about using Continuum in your class. Just one thing to mention to everyone. This is Murphy's Law rearing its ugly head. I uploaded a new installation file for Continuum just before the presentation, where I thought that I had fixed something with this new feature I've just added, and as a result, I broke something. So this, you know, Murphy's Law, you try to make a change quickly before a presentation, inevitably something will go wrong. So it will just take me probably half an hour to fix. But Rob, the version that you've downloaded, you're going to have to install, just download a new version in an hour or so and reinstall. So if you try to open it and you get an error, that's why. But the
actually,
new functionality,
I opened it.
Yeah.
Mine seems to be running.
It will fail if you try to save a file and open it.
Okay.
Yeah. But again, it's a really easy fix. I made it a little hastily before this presentation. Okay, any other questions out there?
Anna, do you have any question?
Okay, well, I hope to see emails from everyone to join the newsletter. Again, Continuum 3 has just very recently been released open source. This is all very new and very exciting. What was that? Oh, maybe that wasn't meant for us. And of course, if you have any questions on the theory, if you have any questions on the software, feel free to email me at continuumwindsoftware@gmail.
If we don't have any more questions, then definitely there will be a question after people go through this presentation one more time, and we'll also upload the PowerPoint on the OpenAI.
Great.
And thank you everybody for participating on this first webinar of our series. And my thanks goes especially to Liz Walls for putting such a nice presentation. And I'm pretty sure many people will benefit from that. I can tell that for sure from my background in industry. Thank you, Liz. Thank you very much. Rob,
Thank
do
you,
you
Rob.
have any more questions?
Not for now. Thank you.
Great. Thank you, Ram. Thanks for the opportunity, and thanks to all of you for your attendance today.
Yeah, thank you very much, Liz. And I would like to thank you, Liz, too, for her support on this presentation.
Absolutely, my pleasure.
With that, we're going to end this presentation today, and we'll look forward to meet you guys in next presentation, probably around 3rd week of January. Thank you very much. Bye-bye.
Thank you.